Hello and welcome to the final part, the video for the final part of the chapter on moments, and it involves sliding or toppling. Okay, so the question is, when we apply a force to an object, will it slide along the surface? Will it slide then topple? Will it topple, or will it do nothing? Obviously, part D is a kind of moot point. I mean, if it's doing nothing, then there isn't really much point at all. So these are the answers which we're going to be these are the questions which we're going to be answering in this video. Okay, so we've got an object, we apply a force to it. Will it slide or topple? And if so, what is the size of the force which we need to exert on the object for that to happen? So I think these are best explained with examples. So let's move that. There we go. We've got an object, a 2 kilogram object on a surface where the coefficient of friction is 0.4. So really what this is about linking together our theories, Coulomb's law of friction, with our theory of moments. So we've got a coefficient of friction 0.4. So this box is 0.5 meters long and 0.2 meters high. That means, and if we're going to put a force, we're going to apply a force at the top left-hand corner there. Okay, because we're now, Mechanics 2 is all about objects have size, it's important to know where that is going to be. Okay, there's going to be the force due to gravity, the usual force to gravity, 2g. Okay, and we're going to have a normal reaction. Now, in M1, because we model the objects as particles with no size, we can put that normal reaction literally on the center of the object, the center of mass, because the center of mass is the object if the particle has no size. Here we've got to be a bit careful. The normal reaction is where the floor is the force of the floor on the box. Okay, and this could change depending. The position of where this force is will change depending on how big P is. Okay, so I've just put it in a generic place there for the minute, and we'll do the analyzing afterwards. Now we're going to get a frictional force of 0.8 G. Okay, because mu is equal to 0.4. So that means that let's go back. That means that the frictional force, the limiting friction, is going to be mu times the normal reaction. So 2g multiplied by 0.4 is 0.8 g. Okay, so that would be that's the size of the limiting friction. So that means when it slides, it's pretty obvious. This is really just from the first chapter that at the moment the p is going to increase. It's going to increase. It's going to increase. There's going to be no movement until p becomes 0.8 g. Okay, when it becomes 0.8 g, it's on the point of sliding. Okay, so at the point of sliding, P is going to be 0.8 g, which is 7.84 newtons. So we know that when we apply a force between 0 and 7.84 newtons, it's going to stay stationary. When it hits 7.84 newtons, the force P, then we're going to get on the point of sliding. And then when it gets larger than 7.84, we're going to get motion, okay, because we'll get a resultant force. Now, let's think about what happens when it topples, because sliding really is what we covered in chapter 1. Now, at the point of toppling, the reaction will be at the bottom right-hand corner, because if you think about it, this object, when it topples, it's going to topple its pivot point, because of P there, it's going to topple. It's going to be pivoted on that bottom right hand corner there. Okay, so that means that now really we need to move on at the point of toppling. Our normal reaction will be right on that corner there. Okay, because that is where the only contact between the object and the floor will be. So the normal reaction has to be from there. Okay, So we're there really. We can take moments about any point to find p. Now it makes sense. Well, let's take it about that point because then that eliminates that 2g. Okay. So what do we have? Well, if we take moments about that point there, this 0.8g, the moment will be 0 because the line of action lies on the pivot point. And what are we going to get clockwise? Well, we're going to get, this p is going to be clockwise. The line of action as it continues is 0.2, so we're going to, moments clockwise is 0.2 times p. Moments anti-clockwise is going to be this force of gravity because that goes around anti-clockwise. And that's going to be 0.25 times 2g. Okay? So, taking the convention that anti-clockwise moments are positive, and we know that at the point of toppling, the moments are going to be equal to each other because we still have equilibrium, we're going to have that the anti-clockwise moment, 2g times 0.25, minus the clockwise moment, p multiplied by 0.2 is going to be 0. Very simple equation to solve. We eventually get that p is 0.5g over 2, which is 24.5 newtons. So for this object to topple, p needs to be increased to 24.5 newtons. Okay, which tells us that as p increases from 0, it will start to slide when it reaches 7.84 newtons. Sorry, I've missed out the newtons there. Cardinal sin. And then it will topple when it reaches 24.5 newtons. So if we're describing the story of this object as p increases, what will happen is, as it goes from 0 to 7.84, it will remain stationary. At 7.84 newtons, there'll be motion. And from 7.84 newtons to 24.5 newtons, the resultant force is going to be increasing, the acceleration is going to be increasing, so it's going to be moving quicker and quicker and quicker at a quicker and quicker rate until it gets to 24.5 newtons, and then all hell breaks loose, and this object is going to topple over. Okay. So, I just pause the video there for a second just to get my second coffee of the day. So, the next 10 minutes, anything could happen. I apologise in advance. Oh, lovely way to start the morning. A couple of espressos. There we go. Right. They're not Costa espressos, so makes a bit of a difference. Right, let's have a look at another example. Okay, here we've got slope. Classic. Okay, first of all, we'll deal with the problem where forces are all horizontal and vertical. Now let's deal with the problem where forces are at angles. Okay, got an object, 60 kilograms this time. Not as big as the heavy child, but still a hefty weight. It's going to experience gravity. Now, here notice my unknown is an angle. My unknown is an angle here. Okay, so if we resolve horizontal and perpendicular to the slope, vertical to the slope, it's 60g cos alpha, because that angle there is going to be alpha. And there we go, the first sign of the coffee kicking in, a bit trigger happy on the buttons. 60g sine alpha is going to be opposite, that's horizontal to the slope. You've got a 60g cos alpha because there's no normal reaction, because there's no vertical motion, and we're going to have a frictional force because the object's going to be sliding down, and the idea is that we're going to increase the idea is that the angle, we're going to increase the angle, and we're going to see what happens to this object. Will it slide? What angle will it slide? What angle will it topple? Now it's 2 meters high. So at the point of sliding, okay, F equals mu r, standard, okay. Now, the frictional force at the point of sliding is going to be limiting friction mu r. Same setup as before, so it's going to be 60g cos alpha. So if we look at equilibrium in direction parallel to slope, we get that F, which is mu times 60g cos alpha, is going to be equal to 60g sine alpha. Okay, so so we're going to get equilibrium. So 60g sine alpha is equal to the frictional force, which is mu times 60g cos alpha, because F is mu times R. Okay, give you a second to digest that equation. Now, this is quite, it looks nasty because we want to find alpha. We want to find out the angle at which that starts sliding. Not a problem really, because actually if we divide by 60g we can cancel. And if we divide by cos alpha, sine alpha divided by cos alpha is tan alpha, which is 0.6. And therefore alpha is arctan of 0.6, which is 31.0 degrees. Now, although it doesn't mention it in the book, or I'm not sure if it mentions it in the book, this is what we call the angle of friction. Okay, the angle of friction. And in general, tan alpha will equal the coefficient of friction. But they don't mention it in the book, so you kind of have to do it from first principles each time. So we know that as we increase alpha from 0, at 31 degrees, this is going to start sliding. Okay? Now, I forgot to mention love length there. There's 5 meters. Let's increase it even more so that it topples. Okay? Now, when it topples, center of mass, okay, because we've got a kind of two-dimensional problem here. The center of mass is going to be acting straight on the point of where it's going to topple. It's going to topple at that point there. Okay, so imagine this angle alpha is where it's going to topple, and that means the center of mass will be acting exactly on that point. As soon as alpha increases even more, the center of mass is going to be, the line of action of the center of mass is going to be going at a point not on the block, where the block isn't touching the surface, so therefore there'll be some toppling. Okay, so really this isn't even a force problem. This is just a problem using trigonometry, because we want the center of mass to act directly on that point there. So at the point of the toppling, the center of mass is directly above the point where the frictional force is acting. Okay, and indeed, actually, as well, the normal reaction will be at that point as well. I mean, I've been a bit blasé. If we look back, I've been a bit blasé about where I've put that normal reaction. I'm legitimate. It's legitimate for me to put it there to start with, because we're not talking about the point of toppling. But I guess really, I should have put that at the point of toppling, that normal reaction should be put there as well. Okay, so the normal reaction should be, there's a line of action there. As it turns out, it doesn't really matter, because to solve this, we can just use the object's dimensions. So this is what we've got here. Okay, the center of mass, which is going to be exactly in the middle of the object. Okay, it's 2 meters high, so it's going to be 1 meter high up there, and along it's going to be 2.5 meters across. Now, if the center of mass acts exactly on the corner, we've got a simple right angle triangle to solve here. Okay, so we know that tan alpha, which is the opposite, 2.5 divided by the adjacent, 2.5 divided by 1, so tan alpha is 2.5 divided by 1, and it's very simple thing to find by the arctan. Alpha is going to be 68.2 degrees. Okay, so we've found the angle at which, if we're increasing the angle of this slope at 68.2 degrees, this object will topple. Okay, and this is the angle of toppling, if you like. So there we have it. These quite fiddly problems, but we're using basically everything we've learned from the first 2 chapters on coefficient of friction, taking moments, and just using a bit of geometry and common sense really as well. I mean, it's just a bit of common sense. Okay, brilliant. Well, what I'd suggest you do now is attempt the exercise 3C on page 58, and that means that we've completed the completed the work here. So really well done. Thank you.